This conference will now be recorded.
Very good evening, students. Today we'll be learning very interesting topics in magnetic effect of current chapter. So the topic we'll be learning today is the magnetic force on charged particle and related topic like Lorentz force, motion of a charged particle in a transverse electric field, transverse magnetic field, and transverse electric and magnetic field, which is the principle of cyclotron. So let us start with our topics today. So first of all, magnetic force on a moving charge. See, we have seen in electrostatics that if you have a uniform electric field or non-uniform electric field, whatever it is, if you have a charged particle here, if it is at rest or static, it is going to experience an electric force. This small a suffix a means electric force, that is q into e. In both cases, this will be q into e, but this force anyway, it will be variable force. So anyway, so this is the electric force. So electric force is experienced by a charged particle when it is at rest, or if it is moving also, the same force will be acting on it. Okay, if it is moving also, it will experience the same force. So in electrostatics, we have seen electric field exert a force on a charged particle. If the charged particle is moving or at rest, doesn't matter, the force will be the same in magnitude, which is given by or exerted by, which is exerted by the electric field. Now here, suppose I have a uniform magnetic field. Magnetic field. See, this cross signs denotes that there is a region where uniform magnetic field is there, but the magnetic field is into the plane of the paper. Okay, into the plane of the paper. So here in this screen, as if the magnetic field lines are just going into the screen, but similarly I can draw another type of uniform magnetic field where I can just give some dots. Okay, some dots. That means magnetic field is just coming out of the screen. And if these are equispaced, then it represents the uniform magnetic field. So this is fundamental idea which we should have while studying magnetic fields. Okay, so this is out of plane, and into plane. Okay, B is into the plane and this is out of plane. So for the timing, let me erase this out of plane. I take into the plane of the paper. So I have a magnetic field, uniform magnetic field. That means everywhere the magnitude of the magnetic field is same, that is B here. Suppose I have a charged particle having charge Q, okay, and mass M, and it is moving with certain velocity. It is moving with certain velocity v and enters into the region where this magnetic field is there. Enters into the region where the magnetic field is there. So, Dutch physicist Lorentz first discovered that when a charged particle is moving through a region of magnetic field, the charged particle will experience a force, and that force is directly proportional to the magnitude of the charge, directly proportional to the magnitude of the magnetic field, and it is directly proportional to the component of the velocity perpendicular to the direction of the magnetic field. So this is in general case. General case, let me tell you, suppose this is direction of magnetic field, and the charged particle starts moving from here with the velocity v, okay, v, and making an angle theta with the magnetic field. So this will have two components, one along the magnetic field, that is v cos theta, which is sometimes called v parallel component, like this, and another component is v perpendicular. Okay, so that v perpendicular component is v sin theta. So this component is v sin theta. This is perpendicular to the direction of the magnetic field. So I have taken the component of the velocity component of the velocity which is perpendicular to the direction of the magnetic field. So this is the statement that, let me tell you, this is magnetic force Fv. So magnetic force on the charged particle is directly proportional to Q, directly proportional to the magnitude of the magnetic field, and directly proportional to the component of the velocity which is perpendicular to the magnetic field. So if we combine all of them, then what we get? We get Q B V sin theta, and for the time being, or it is somehow seen, or it is observed that the proportionality constant to be unity. So this is Q V B and sin theta. Okay, and if we write in terms of vector, so it will be Fv is equal to Q into V cross B. So V cross B means VB sin theta along with some direction. Okay, so this is how we found out that the magnetic force on a charged particle, the charged particle is moving with the velocity v, making an angle theta with the direction of the magnetic field. So in that case, the magnetic force will be Fb is equal to Q V cross B. Okay, Q V cross B. Let me now tell you how to find out the direction of the magnetic field. Sorry, direction of the force, magnetic force. So how to find out the direction of the magnetic force? So there are different rules for finding out the direction of the magnetic force exerted by the magnetic field, and one among them is a right hand thumb rule. Right hand thumb rule is one among the rules which will help you to find out the direction of the magnetic force. So in this case, look, v is the velocity of the charged particle and b is the magnetic field. So if I have two vectors, see in the VB plane, so this V and B, they are in plane, in the same plane, okay? In the same plane. V and B are in the same plane. So according to this right hand thumb rule, you have to stretches your 4 fingers. See these 4 fingers you have to stretch along the direction of the first vector in the cross product. This is actually all applicable in case of any kind of cross product. So you have to stretch your 4 fingers along the, see first you have to stretch your fingers like this along the first vector, and then you have to curl your finger along the direction of the second vector. Here the second vector is B, right? You look here, first the fingers were like this, okay, stretched along the direction of B, then they were actually curled like this. And at this situation, when you do this job, your thumb will direct you in the direction of the magnetic force or any cross product. So the thumb will give you the direction of the product. Okay, so here see F is actually FB here in this case if you look here. Okay, so this is the rule which we are going to use in every case or in most of the cases to find out the magnetic force on a moving charged particle. Okay, all right, so I'll just summarize here what we have seen. We have seen magnetic force on a moving charged particle. Okay, if the charged particle has charge q, mass m, and it is moving with the magnitude, like with the velocity of magnitude v, but the velocity is making an angle theta with the direction of the magnetic field. So in that case, see, we will have two components of the velocity. So one is v parallel along the direction of the magnetic field, that is v cos of theta, and another one is v perpendicular, which is along this direction. Okay, v perpendicular, that is v sin theta. Okay, so the magnetic force depends on directly on the magnitude of the charge, magnitude of the magnetic field, and the component of the velocity, which is perpendicular to the direction of the field. So these were the things which we need to know. So this force was actually first discovered by Lorentz. He was a French, or Dutch physicist. Okay, Dutch physicist. Now we'll see when a charged particle is moving in a uniform but transverse magnetic field. So transverse magnetic field, I was already drawing in the first slide itself. See, transverse means what? If suppose this is the direction of motion of the charged particle, transverse means perpendicular to that. Okay, so magnetic field will be in the direction perpendicular to the direction of the velocity. Okay, this is actually transverse magnetic field. If the charged particle is moving in this direction, okay, along the horizontal x direction, and then B will be either in the vertical direction, like y direction or z direction. So that is actually transverse magnetic field. Now look here. So if a charged particle enters into a region where there is a uniform magnetic field in a direction perpendicular to the direction of the velocity. See, this is velocity vector. So this is velocity vector. The direction of the velocity vector is this, and you know the magnetic field is now into the plane of the paper or plane of the screen here. So you know this velocity vector is perpendicular to the direction of the magnetic field. Now we know since the charged particle is moving. Okay, so one more thing I just forgot to tell you. See, from here we can easily understand that the magnetic force will be 0 if V is 0. That means for a static charge, magnetic field doesn't experience exert a force. Okay, so for a static charge, magnetic field does not exert any force. That is, F is 0 when V is 0. One more case we can have, if suppose the magnetic field direction is B and the velocity also has the direction along the direction of the field. So in that case also the charged particle will not experience any force because theta is 0 here in this case. And see, we know magnitude of the force will be Q, V, B and sine theta. If theta is 0, then also this magnetic force will be 0. So there are two cases when charged particle will not experience any force in a magnetic field. One first case is if the charge is static. Okay, static charge when the velocity is 0. Okay, these are the cases. And second case is that, so this is case 1, and case 2 is that if the direction of velocity of the charged particle is parallel to the direction of the magnetic field. In that case also the charged particle will not experience any force. So this will be 0 here. Okay, so these are two cases I need to tell you. Now here we will see, so we have, see, magnitude of the force Q V, okay, Q V B sine theta, Q V B sine theta. Now in this case, so this theta is actually the angle between B and V, right? Velocity vector and magnetic field vector. Okay, now in this case, see, the magnetic field is into the plane of the paper and it is in the plane of the paper. That means here now magnetic field and the velocity vector has an angle theta is equal to 90 degree. That means the magnetic force on the charged particle will be maximum here. Okay, so it will be maximum QVB sine 90 degrees 1. Okay, so this is the maximum force. So maximum force will be experienced by the charged particle. One point to note here. Second thing, magnitude is done, but what will be the direction? According to my right hand thumb rule, what will be the direction of the magnetic force here acting on the charged particle? Look, if we apply, see, suppose this is my magnetic field, okay, into the plane of the paper. Now if you apply this B cross B, so stretch your 4 fingers, okay, 4 fingers like this, and then curl it. So you will see your thumb will direct towards the center, okay, towards this way. Okay, so at each point, if you see your magnetic, this force is always tangential to this and in the plane itself. So this force will be maximum and the value of the force will be always same. Okay, same force will be acting, and see, direction will be always towards this direction. Okay, towards this, like this, like this. So one more point we need to find, need to note here is that, so if a charged particle is moving in a uniform and transverse magnetic field, its trajectory will be a circle or circular path. Trajectory, or the path along which the charged particle will move, will be a circle. trajectory will be a circle. Okay, so in this case, two things we have learned, that the magnetic force, if the velocity vector is making an angle 90° with the magnetic field, then magnetic force exerted by the magnetic field on the charged particle will be maximum, that is qvb, and direction of the magnetic force will be such that the force will make the charged particle move in a circular trajectory or in a circular path. So there can be a question, if a charged particle moves in a like or enters in a region of transverse magnetic field, then what will be the path of the charged particle, or yeah, what will be the trajectory or path of the charged particle? That will be circle. Okay, that will be circle. All right, if it is a uniform magnetic field, if it is a uniform magnetic field and the charged particle enters such that the velocity vector and magnetic field vector are perpendicular to each other, so in this case circular trajectory will be there, circular trajectory. Okay, or circular path. So these things are done. So in this case, look, for circular motion you require a centripetal force. So what is the source of centripetal force here? So we can see the magnetic force. In this case, magnetic force is the source for centripetal force. As I was showing you, that the force will be always acting towards the center of this circle. See this, at this point like this, at this point, see this is V, this is F, this is V, this is F, this is the force. This is the force which is acting always towards this fixed point O, say. So this is V, this is V, this is the force which is acting towards the center. Okay, so it will always, so this is the force which is, this magnetic force is actually supplying the centripetal force to make the charged particle move in a circular trajectory. So I have got that here the centripetal force Fc is provided by the magnetic force. Okay, so suppose the charged particle has a mass, charged particle has mass, charge has mass, mass m, and charge q. Then see, we can actually find out what will be the radius if the magnetic field, magnitude of the magnetic field, magnitude of the velocity, and the amount of charge is known. We can actually estimate what will be the radius of this circular trajectory and what will be the frequency or time period of revolution of the charged particle. So there will be a nice physics out of it. So let us find out few parameters over here for a circular trajectory. So see, Fc is actually given by the magnetic force. So for a, like from the mechanics, what we know, Fc centripetal force mv square by r. If m is the mass of the charged particle and if the radius of the circular trajectory is r, so mv square by r. So this will be provided by q, v, and b. So from here, one v can be cancelled from this. So we will be able to find out what is v, what will be the speed. Okay, or if we know the speed, okay, let me just find out uh, the speed itself. So m, sorry, q, b, and r by m, or r circular. Suppose we want to know what is the radius of the circular trajectory, so mv by qb. So this is the parameter which we may have to find out for some cases in practical purpose. So what we need to know? We need to know the mass of the charged particle, velocity of the charged particle, and magnitude of the charged particle, and magnetic field, magnitude of the magnetic field of the charged particle. By knowing that, we will be able to control, or by controlling V, B, or any of the parameters, any of the four parameters, we can actually control the radius. Okay. So once we know the radius, can we find out time period? Time period for circular path, see 2 pi r by v. Okay, 2 pi r by v. So v we had found out here. Look here, or either uh, we can we can we can put the value of r also. Let me keep this v alone here. So this is mv by qb. So v goes off. So 2 pi m by qb. Okay. So just putting the value of r here, we get time period. So here I'll write the parameters what I'm getting. See, okay. So let me just erase this part. We have understood this. So I'll write down the parameters what we're getting. So we have got this radius of the trajectory, circular trajectory will be given by or obtained from here, mv by qb, and time period will be obtained from the formula 2 pi m by qb. Okay. So time period, in both cases you look, mass is a factor, then qb is a factor, q and b, charge and magnetic fields are factors. Okay. Now what will the frequency? So frequency can be found out. Frequency of oscillation will be, or frequency of the revolution will be, see, this will be 1 over t. 1 over t means qb by 2 pi m. So these are the parameters. Sometime you may have to calculate or find out in your exam. Okay. So if angular frequency is being asked, you can find out from here itself. Angular frequency. How do you find out? 2 pi f. 2 pi f. So if you multiply 2 pi with this, so 2 pi will cancel out. Okay. So qb by 2 pi m. So this will cancel out each other, and then finally what we get, angular frequency will obtain as qb by m. qb by m. So these are four parameters we can find out from here. Okay. See, one more thing we can find out. Okay. So okay, this we'll discuss later again. So these are the parameters we found out from here. Okay. So this is when a charged particle moves in a uniform transverse magnetic field. Okay. But suppose the charged particle is moving in a uniform transverse magnetic field, but making an angle with the magnetic field. So earlier we had seen that magnetic field and velocity vector of the charged particle, they are making an angle theta is equal to 90 degree. But suppose this is not 90 degree. If the charged particle enters with certain velocity, making an angle theta with the magnetic field direction. Suppose in this case, in this figure, look, if suppose magnetic field is acting along the x direction, and the charged particle which enters into the region of magnetic field making an angle, see, velocity vector of the charged particle is making an angle theta with the magnetic field direction. Here also you can see. So this is, so as I was showing you earlier, so velocity will have two velocity components. So velocity will have two components, one along the direction of the magnetic field, another along the direction of the direction perpendicular to the magnetic field. So this is perpendicular component, this is parallel component. So we can write perpendicular components and parallel components. So V sine theta, perpendicular component, and parallel components are, parallel component is, sorry, let me write here itself, V cos of theta. So as I was discussing earlier, the charged particle, since it is having two velocity component, one is parallel to the magnetic field, another one is perpendicular to the direction of the magnetic field. So here the circular, the trajectory of the charged particle will not be circular. It will be something different, that is helical path. Path will be helical. So trajectory will be helical. So how to find out, like how to realize whether this the path will be helical or not? See, in this case, the charged particle starts from the origin. It is, see, earlier, like in the beginning, it was moving along this direction, which is making an angle theta with the magnetic field direction. But it has two components of the velocity. One is parallel component, another one is perpendicular component. This parallel component is not affected by magnetic field. Since it is parallel to the magnetic field, it is not affected by B. Okay, not affected by B. That means charged particle is not going to experience any force due to this component of the velocity. Okay, so what happens, the charged particle will move. So this means charged particle will move with a uniform velocity, uniform speed. We can write uniform speed, that is what, V cos theta along x-axis or along the magnetic field direction. Okay, according to this figure, it is x-axis. What about this velocity component? Since it is perpendicular, it will be actually compelling the magnetic field to exert a magnetic force on the charged particle. So I have now, see, x direction, you have V, you have V sine theta or V perpendicular. Along the y direction, okay, this is x direction. So you will experience, like charged particle will experience a magnetic force that is Q V B sine theta. This will be the magnitude of the force. And what will be the direction? The direction will be, see, this is V cross B, right? This is J cross I. J cross I. Okay, V cross B. That means, see, I J K. So I J K. This is cyclic role. So if I go J cross K, I'm sorry, J cross I, that will give you minus K. That will give you minus K. J cross I will give you minus K. So force will be acting in the Z direction, negative Z direction. Okay, negative Z direction, as you can see. But at the same time, so if Z is this way, then negative Z. So it will be experiencing a force along this direction, but at the same time, the charged particle will move along the x direction. Okay, So it will be moving this way also and this way also. So, and another point is that since this velocity component is perpendicular to the magnetical direction, it will actually try to make the charge particle move in a circular path in the YZ plane. Okay, in the YZ plane, in the vertical plane. Since V and B are okay, so the charge particle will try to make it move in the vertical, like in the YZ plane, as you see in this figure. Okay, so because of this perpendicular component of the velocity vector, the charge particle will experience a force in the negative z direction, which will act as a centripetal force and try to make the charge particle move in a circular path. But see, if I go like this, then it is a circle. But suppose when I start from here and come back to this point, by that time, due to this V parallel, the charge particle moves up to here. Okay, so the path will be actually a helical path like this. By the time the charge particle make a complete revolution, the charge particle itself is moving forward, okay, along the x direction. So that's why the path will be a helical path instead of a circular path. Okay, trajectory will be helical. So there are two things when we can have helical path. One is this. Okay, we'll see another one. This is helical path, but on another case we will get a spiral path. Okay, so we'll discuss that also. So I hope you have understood how we are getting a helical path in this case. So since it is circular motion, so we'll get the same expression for the radius of the helix. See, we have mv by qb. The same thing we'll get here, mv by qb. This will be the radius, frequency, time period, everything will be the same. Okay, time period, frequency, everything will be same. All right, 2 pi r by v. So 2 pi r is mv by, so it will be 2 pi v, 2 pi vv will go away, 2 pi m by qb. So this will be time period and etc. You can find out. Now one more point is, or one more parameter in this case of helical path is important, that is pitch. How do you get a pitch? Or first of all, what is pitch? See, pitch is actually the linear distance a charge particle moves in a complete cycle. In a complete cycle, suppose the charge particle was here. Okay, so when it moves in a complete, like after complete revolution, it reaches here. So the distance between this uh, distance between these points, or we can say distance travel during a complete revolution. As I was showing you, that by the time it completes a full rotation or full revolution, the charge particle moves to other point. So the distance between the initial and the point after, like point where it goes after completing one revolution, is actually called the pitch of the helix. Okay, so pitch of the helical path, how to find out numerically? So this linear distance we have to find out. So we know the time period for revolution. complete revolution, and it is moving along the x direction with uniform velocity. So this is t into v cos of theta. So what is t? You can find out. So t is actually 2 pi r by v. Okay, time period. Okay, time period is 2 pi r by v. So that you have to see. Actually, this is 2 pi m by cube. This is time period only. Okay, this is time period. Okay, so I hope that that is the thing. So 2 pi m by qb. So that is actually time period. So 2 pi m by qb into v of cos theta. Okay, this value you have to multiply. You have to multiply the velocity or the speed parallel to the magnetic field with the time period, so that you get screw pitch. Pitch is actually denoted by p maybe. Okay, so pitch, not screw pitch, sorry, this is pitch of helix or helical path. Okay. So what we have learned, I'll summarize here. We have learned that if a charged particle is moving in a uniform transverse magnetic field, a uniform magnetic field, but the velocity is making an angle theta with the magnetic field direction, then the path will be, or trajectory will be, helix or helical path. Trajectory is a helical path. And see r, t, f, omega, this you can find out using the same formula, same thing, fc is equal to fb from this particular idea. And how do you find out pitch? This is the linear distance or length of the path the charged particle moves in a single revolution. Okay, so that is given by t into v of cos theta. Okay, so that will be 2 pi m by q b v of cos theta. So this is the thing. Now we'll move on to an important topic now, that is the motion of a charged particle in a crossed magnetic and electric field. Okay, crossed electric and magnetic field. Let us go to directly to the point. So what is the point here? See, suppose there is a region where magnetic field is along the z direction and electric field is along the y direction, and a charged particle having charge q and mass m is entering into the region with the velocity v, and the velocity is along the x direction. That means both are transverse to the velocity vector. See, velocity vector is perpendicular to E as well as perpendicular to B. That's why it is called transverse or cross electric and magnetic field. And also one more point you need to note here, that E and B both are also perpendicular. That's why. So when we have electric and magnetic field perpendicular to each other, we are saying that as crossed electric and magnetic field. Okay, crossed electric and magnetic field. Crossed electric and magnetic field. Okay, crossed electric and magnetic field. So here both the electric field and magnetic field are perpendicular to the velocity vector. So we know. Okay, so this thing, let me first tell you. I have forgotten to tell in the beginning itself. See, when a charged particle is moving both in a in a region where both electric and magnetic field are there, So what will be the force on the charged particle? Force, there will be two forces. One is electric force, another one is magnetic force. So magnetic force will be given by Q B cross B. And see, in electric field, if there is electric field and there is a charged particle will definitely experience a force whether it is in motion or at rest. So here the electric force is this. Okay. So these are two forces. Now both electric and magnetic fields are there. So the charged particle will experience a net force which is called Lorentz force. Earlier the force, so this force is magnetic force, but combination of this electric force and magnetic force is called the Lorentz force. This is Lorentz force. Okay, this is Lorentz force. Q into E, electric force plus magnetic force. So electric force plus magnetic force is called Lorentz force. Okay, now I have told you all these things. Let me just clean this portion, except keeping this. Okay, now we'll try to find out what is the direction of this force, Lorentz force here. So we'll just write this Q. See, let us say the magnitude of the electric field is E and it is acting along J cap direction. Okay, and then I have Q V cross B. V is acting which direction? X direction. So V is along X direction, and B is actually along K direction. Okay, now let us simplify a little bit. Q E J cap here plus Q V and B, these are magnitude. We can just bring it out. Okay, only thing is this I cross K. Cross product of this will give you the direction. See, I is a K, cyclic rule we will go for. So I cross K will give you minus. So see, I'm giving this arrow direction. That means if I write I cross J, then you will get positive K. Okay, positive K. If other way, that will be giving you negative. So in this case, I cross K, which will give you minus J cap. Okay, so the magnetic force, look here, the magnetic force will be acting. Magnetic force will be acting. I'm sorry. Magnetic force will be acting along the negative J cap. Okay, along the negative J cap. Or if we again simplify, then it will be Q E minus Q V B along J cap. Okay, so magnetic force, you look, this is along minus J cap direction, and this is, see, force, electric force is acting along positive J direction, negative Y direction and positive Y direction. So if somehow, see, if somehow the magnitude of V, B and Q are adjusted, if somehow the value of Q, V, B are adjusted in such a way that the magnitude of the electric force and magnitude of the magnetic force become equal. So in that case, we can write E is equal to VB. See, if they are actually becoming equal to each other, that means the charged particle will not have any force on it. Even though charged particle is moving inside or moving through a region where cross electric and magnetic field is present, but it will not experience any force due to both of electric and magnetic fields. When when this is 0, that means when the magnitude of the electric force and the magnitude of the magnetic force are becoming exactly equal to each other, then the charged particle will move with charged particle charged particle will move undeviatedly. Okay, undeviated. That means its direction will not change, right? It will just move along the x direction itself. Since no magnetic force, no electric force, so it will actually move undeviatedly. Okay, so the motion of the charged particle will not be deviated if the magnitude of the electric force and magnitude of the magnetic force, they are becoming equal to each other. I'll write down once again. So what is the condition for this? For no deviation in a cross electric and magnetic field, there will be a question: what is the condition for no deviation, or a charged particle is moving in a uniform, like in a cross electric and magnetic field? So what is the condition that charged particle will move undeviatedly, or there will be no deviation of the path of the charged particle? Okay, so this is q vb is equal to this. So E is equal to VB, and from here we can find out. See, we can find out a typical velocity. A typical velocity, if we know the value of this E and B. If we know the value, see, we can adjust electric field. This is in my hand. This is also in my hand. I can adjust in such a way that the velocity is exactly becoming the ratio of electric field and magnetic field. So in this condition, charged particle will move without any deviation. So that's why this particular arrangement is called velocity selector. Velocity velocity selector. This particular arrangement will be called as velocity selector. There are few applications of this particular principle, velocity selector. So what is the velocity of the velocity selector? That should be E by A. Sorry, E by B. It magnitude of the velocity should be equal to the ratio of electric field to the magnetic field. So that is the condition for no deviation in a crossed electric and magnetic field. And you could understand what is called velocity selector. I'll tell you why this velocity or this particular arrangement is called velocity selector. Okay, suppose you have mixture of gases. So so application of velocity selectors, what are the applications? Actually, this arrangement was used. This arrangement was used by J.J. Thomson. J.J. Thomson. Okay, so this arrangement was used by J.J. Thomson to find the value of E by M ratio. Okay, E by M ratio. And see, nowadays we use mass spectroscopy, mass spectroscope. Okay, mass spectroscope, which uses this principle of velocity selector. Okay, principle of, or this fact of velocity selector. Sorry. Okay, so I'll tell you. So in the mass spectroscopy, there could be a mixture of suppose helium, hydrogen, and many other gases, argon, etc. So how to find out which gas, like what are the gases present in a mixture, or whether helium is there or not? How to find out that? See, each has their masses, right? Each gas has their masses. So according to masses, they will have different velocities. Okay, different velocities. Okay, different velocities will be there for different gases. That is for sure. Now, if we adjust in such a way that the velocity of this is becoming velocity of the gases, a particular gas is becoming exactly equal to this E by B ratio. So we have to adjust E by B ratio such that we like some of the charge particle will have velocity exactly equal to this ratio. Then that particular gas will pass through the spectroscope and you will be able to detect that. So this is the use of velocity selector. Actually, we'll stop it here. We'll not go for the cyclotron today. In the next class, we'll discuss the cyclotron and possible applications. We'll discuss application of cyclotron and we'll try to discuss typical numerical problems from JEE, mains and advanced on this particular topic. Okay, so thank you for your patience. Bye for today.
This conference will now be recorded.